So today I will introduce to you my work in statistical security for Internet of Things. Actually, I'm a first year PhD student, and this is my work so far. So first we will introduce the IoT security problem. And after that, we will introduce the motivation behind our work. And then we will introduce what we did so far. So as we can see, the IoT security problem is an emerging problem nowadays because of first, the total number of active IoT devices connected worldwide is expected to increase by 22 billions by 2025. So what's the problem of that? The problem that we have very poor IoT security measures, especially in the IoT devices we use in the high-density applications. So, as we can see, we have 90% of the devices collected at least one piece of personal information, and also 70% of devices used an encrypted network service. 70% of the devices along with their cloud and their apps enable an attacker to identify a valid user accounts, and 80% of the devices along with their cloud and mobile applications fail to require password of sufficient complexity. And also a recent research showed us that there is 25 vulnerabilities in the most 10 used IoT devices in the world. So all these vulnerabilities lead to a lot of IoT security incidents in the recent years, as we can see from the chart developed by Cyber Threat Report in 2019, that in 2018, the cyber attacks increased by 200% than the cyber attacks in 2017, which is a really very big number. We can remember the ransomware attack happened in the NHS and caused the NHS to lose like 63 billion pounds. In order to fix and to install high security devices along the NHS. And the funny thing that thirds of the devices infected by the ransomware were IoT devices used in the health sector. Also, we can remember the famous Mirai attack, which happened in 2016 and led to most of the East Coast in the US lost its connectivity to the most popular internet service providers like Amazon and Facebook. So the Mirai botnet was a distributed denial of service attack, and it used, along with routers, it used CCTV cameras, which the problem with CCTV cameras, it has a default password and username used with it. So, as we can see from this chart, that the traffic, this is one of the traffic in the infected companies with Mirai in 2016. And we can see here, sorry. We can see here the normal behavior. We can see here a low traffic, and there is several attacks.
Just reset these.
And there is several attacks up to 250 gigabits per second. So if we had a mechanism to in the IoT device itself, in order to know that this device is behaving abnormal, is not behaving in a normal way, so we can, and then we have a mechanism to block this device. Then we could save like millions or yeah. So what is the solution? One of the solution for this is not the only solution, of course. One of the solution is anomaly detection. And as we can see, the anomaly detection is to find the anomalous behavior to find the anomalous behavior of one dimension at some points, and then to declare anomaly. So to have the anomaly detection, we should know the normal behavior, and then we could know if there is anything go wrong with in any time after that. So what is the challenges for IoT for anomaly detection in the IoT setup? One challenge is the anomaly detection in the high density IoT networks, in the massive IoT, because we are using low cost and low energy and massive numbers of IoT devices. So what happens that we have low cost and low energy devices, so we could not do very complicated security measures at the device end. And also, we have a very high number of devices used, massive numbers. So this means a huge data we should process in order to know the normal and then the anomalous behavior. So, in order to make this problem simple, we want to develop a distributed IoT anomaly detection method that is not complicated, not computationally complicated, and also it can be done in the device end, so it can use the device data only, and it doesn't need to use the other devices in the network data. So the problem with that is the modeling of the normal and the anomalous behavior of the IoT device. We can see from the chart here, we have the normal behavior and the anomalous behavior on the other side. The normal behavior, we describe the number of packets per second in one day. For this device is a motion sensor. We took this data from, we have the data source downside. So So as we can see here, the volume of the traffic is not high in the first chart, and it is very high in the second chart, but it is very bursty. That means we have the number of packets sent per second by the motion sensor is from 0 up to 80 packets per second. And in the other side, in the normal behavior, it is from 0 to 20 packets per second. And as we can see, we cannot, if we want a real-time detection for this scenario, we cannot fix like a mean and said if it is above this mean, then we have an anomalous behavior, or if it is down this mean, we have a normal behavior. So we should characterize as well the inter-arrival time and also the number of packets sent per second together. So as we can see from the two challenges we described before, we need a real-time and a distributed algorithm, which is not very complicated, and we need also to use we need to use not a high volume of data. So the IoT security suggested scheme. The first, this is our work, is a statistical solution. The first chart, this is the number of packets sent to each IP. This is the number of packets sent to each IP address. In the first chart, we can see the IP address here is the IP address of the gateway, which has the highest number of packets sent. And in the second chart, where is the attacked traffic, we have lots of other IP addresses. You can see that this is not the normal behavior from this chart. So what is our solution? Our suggested solution is So our suggested solution is do the queue modeling for the income traffic. First, we cluster the income traffic into different packet sizes, and each packet size we have a stream of traffic. We enter it into a queue that have a service time which is greater than the mean arrival time of the packets, and then from this we can model the delay or the queue size. You can see the chart down. You have the queue size per second, as you can see, it is coming up and going down depending on the number of packets sent per second. So we can see the difference between the normal behavior and the anomalous behavior when we use our method. So in the normal behavior, you can see that the queue is building up and emptying, and within a certain range. And for the this type of attack, this queue is building up infinitely. And as you can see, we set up a threshold. So after this threshold, we assume that every point after exceed this threshold is regarded anomalous point, and so an attack can be declared. How we can choose the threshold? We can choose the threshold of from the complementary CDF of the delay we modeled earlier. So what we did is for 30 days, we have a complementary CDF for each day. And from this complementary CDF, we set up a reasonable threshold. And then we have the mean for 30 days. And as you can see, when we set up the threshold, it was, in this case, 1,250. We declared an anomaly in 7,000 seconds. And it was 2,000 seconds later than the actual attack. So we can always reduce the threshold, so we have an early detection, but there is a trade-off between the early detection and a false positive alarms in some cases. Yeah, so the future work is to develop simultaneous queues for different package sizes. So in our analysis, we used just one stream of packet size, which was for the TCP protocol for our IoT device, and also reducing the difference between the detection and the actual attack time by selecting optimum threshold, updating threshold with time. So because we know that the behavior of IoT devices is not uniform in most cases, like, for example, in the motion sensor or in the IP cameras, or we have a normal behavior that changes with time slightly. And also, we are starting to develop our own test bed and assess the real-time application of our algorithms. Thank you.